Welcome to the Greek ship corrosion channel. My name is احتشام زاده. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 2, Thermodynamics of electrochemical reactions. In this video, the change in the Gibbs free energy, the value of Gibbs free energy, the Gibbs free energy of formation, and the standard Gibbs free energy change for chemical reactions. The reference is Fundamentals of Electrochemical Corrosion, ASM International. The change in the Gibbs free energy. In chemical thermodynamics, the process of frequent interest is the chemical reaction abbreviated as A molecules of A plus B molecules of B reacts to yield C molecules of C plus D molecules of D. The change in the Gibbs free energy for a finite amount of reaction at constant T and P may be written as delta G is equal to delta U plus P times delta V minus T times delta S is equal to delta H minus T times delta S. In principle, U internal energy, H enthalpy, and S entropy, from which G may be calculated, exists for each chemical species. Also, P is the pressure and V is the volume. If these values could be determined, then the change in the Gibbs free energy could be calculated for the reaction as follows. Delta G is equal to delta U plus P times delta V minus T times delta S is equal to delta H minus T times delta S. The Gibbs free energy of the reaction is equal to the Gibbs free energy of the products minus the Gibbs free energy of the reactants. Delta G reaction equals C times GC plus D times GD minus the sum of A times GA and B times GB, where GA, GB, GC, and GD are the Gibbs free energies per mole for each species indicated by the subscript. If the calculation leads to delta G less than 0, then the reaction, as written left to right, is capable of occurring spontaneously. Although this equation suggests that absolute values of the GFEs or Gibbs free energies of the chemical species can be obtained and that these values can be used to calculate the change in the Gibbs free energy for the reaction, such absolute values cannot be determined. The reasons are: 1. The Gibbs free energy is derived from the internal energy U or the enthalpy H, neither of which can be assigned absolute values. 2. As a consequence, the Gibbs free energy can be assigned a numerical value only relative to its value in some reference state. 3. The usual reference state is the stable form of the substance at the reference condition, these usually being 1 atmosphere pressure and either 0 Kelvin or 298 Kelvin. 4. Since the absolute value of G in the reference state cannot be determined, an arbitrary value must be assigned. 5. A consistent basis for calculations results if the GFEs of the elements in their stable forms at the reference conditions of 1 atmosphere pressure and 298 Kelvin are assigned the value of 0. 6. The pure elements at other conditions will have definite values. For example, the Gibbs free energy change at temperature T is equal to the Gibbs free energy at temperature T minus the Gibbs free energy at the reference temperature. 7. When the Gibbs free energy of a chemical compound is needed as a function of temperature, its value at the reference temperature also could be assigned a value of 0, and values at other temperatures calculated relative to the reference temperature just as for pure elements. However, as discussed next, the Gibbs free energy of a compound can be referenced to the elements that compose it. This reference method is used in most calculations involving chemical reactions. 9. Any reaction between elements to form compounds has associated with it a change in the Gibbs free energy between the compound and the reactant elements. 10. Thus, for oxidation of iron at temperature T, we can write 4/3 of iron plus oxygen reacts to yield 2/3 molecules of Fe2O3. The Gibbs free energy formation at temperature T is equal to 2/3 of the Gibbs free energy of Fe2O3 minus 4/3 of the Gibbs free energy of iron minus the Gibbs free energy of oxygen. Delta GFT is the Gibbs free energy of formation at temperature T and at the particular conditions of the reaction. In this case, the only important variable other than temperature is the pressure of the oxygen, since the other two species are solids of fixed composition whose GFE is essentially independent of pressure. If the reactant elements and the product oxide are in their stable forms at 1 atmosphere, the symbol delta G naught FT is used to indicate the standard Gibbs free energy of formation at temperature T. Standard values are usually reported for reference temperatures of 0 Kelvin and or 298 Kelvin. In general, standard Gibbs free energy of formation at the reference temperature values are based on calculation from direct experimental reactions of the elements to form the compound and from specific heat and related calorimetric measurements on each species, which allows correction of the data from T experimental, that is, the experimental reaction temperature, to the reference temperature. Tabulations of standard Gibbs free energy of formation at 298 Kelvin or standard Gibbs free energy of formation at 0 Kelvin for reactions and of the specific heats of reactants and products to allow temperature corrections form the source from which many chemical thermodynamic calculations are made. Calculation of standard change of Gibbs free energy for chemical reactions from Gibbs free energy of formation. For chemical reactions in which all of the reactants and products are in their standard states, the change in the Gibbs free energy for the reaction is given by the standard Gibbs free energy of the reaction is equal to the sum of the standard Gibbs free energy of formation of the products minus the sum of the standard Gibbs free energy of formation of the reactants. For example, in considering the oxidation of Fe3O4 or magnetite to Fe2O3 or hematite by water, Fe3O4 plus half a molecule of water reacts to yield 3/2 molecules of Fe2O3 plus half a molecule of hydrogen gas. The standard Gibbs free energy of the reaction is equal to 3/2 standard Gibbs free energy of Fe2O3 plus 1/2 of the standard Gibbs free energy of H2 minus the sum of the standard Gibbs free energy of Fe3O4 plus 1/2 of the standard Gibbs free energy of water. Absolute values of Gibbs free energy are not available and the above calculation cannot be made directly. If the equation 1 is correct, it is necessary to show that the following equation is equivalent to the equation 2. The standard Gibbs free energy of the reaction is equal to 3/2 the standard Gibbs free energy of formation of Fe3O4 plus 1/2 of the standard Gibbs free energy of formation of H2 minus the sum of the standard Gibbs free energy of formation of Fe3O4 plus 1/2 of the standard Gibbs free energy of formation of water. The reactions for the formation of the compounds and expressions for the standard free energies of formation are 3 molecules of iron plus 2 molecules of oxygen reacts to yield 1 molecule of magnetite or Fe3O4. The standard Gibbs free energy of formation of Fe3O4 is equal to the standard Gibbs free energy of Fe3O4 minus the sum of the standard Gibbs free energy of iron and the standard Gibbs free energy of oxygen multiplied by the coefficients. And the next reaction, H2 plus half a molecule of oxygen reacts to yield water. The standard Gibbs free energy of formation of water is equal to the standard Gibbs free energy of water minus the sum of the standard Gibbs free energy of hydrogen gas plus the standard Gibbs free energy of oxygen multiplied by the coefficient. And the other reaction, 2 molecules of iron plus 3/2 molecules of oxygen reacts to yield 1 molecule of hematite or Fe2O3. The standard Gibbs free energy of formation of hematite is equal to the standard Gibbs free energy of hematite minus the sum of the Gibbs free energy of iron plus the standard Gibbs free energy of oxygen multiplied by the coefficients. The standard Gibbs free energy formation of hydrogen is equal to 0 as an arbitrary reference value. When the standard Gibbs free energy of formation expressions are substituted into equation 3, equation 2 is produced. Thus, the standard Gibbs free energy of formation data can be used to calculate the standard Gibbs free energy of the reaction through equation 1. Conclusion. This equation gives the Gibbs free energy of reaction when reactants in their standard states are converted to products in their standard states, an initial calculation usually applying to the reference temperature for which data are tabulated. From specific data, the change in the standard Gibbs free energy of formation of each reactant and product with temperature may be calculated. The values of the standard Gibbs free energy of formation at 298 Kelvin can then be corrected to the standard Gibbs free energy of formation at temperature T, where T is the reaction temperature of interest. 4. The new set of values of the standard Gibbs free energy of formation at temperature T is then appropriately combined to give the standard Gibbs free energy of the reaction at temperature T for any reaction. Spontaneity direction of a reaction. The condition for a reaction to occur spontaneously, however, is not that the standard Gibbs free energy of reaction delta G naught prime of the reaction at temperature T is negative, but rather that the change for the actual conditions of the reaction delta G of the reaction at temperature T is negative. The Gibbs free energy of the reaction at temperature T is calculated from the standard Gibbs free energy of the reaction at temperature T by correcting the latter for the differences in concentrations of reactants and products from those of the standard state to those of the state corresponding to the actual conditions of reaction. Then, if Gibbs free energy of the reaction at temperature T is less than 0, the reaction will occur spontaneously. Thank you for your attention. Challenge number 12. If you like to challenge yourself, please answer this question in the comments below. What does the Gibbs phase rule state?